Hi, my name is Kennedy, and this is my Lab 4. For this lab, we analyzed the motion of a spring mass system where the mass swings in an arc while oscillating on the spring. We used Tracker to track the position of the object as it oscillates. And then we used GlowScript to get the computational prediction. We compared the prediction and the observed motion of the mass. And then we also plotted energy changes in the model, which include changes in kinetic, gravitational potential, spring potential, and total energy. Overall, this lab was to help familiarize ourselves with the effects of a spring mass system and how it should act. Some important concepts to note are Newton's second law, which plays an important role on the acceleration of the spring as it is released, and then the rope swing equation, which mass times change in velocity over change in time equals the net force, and then how weight force equals the mass and the rope force acting on the system, and then how the ropes stretch with the spring-like forces between each atom, allowing us to treat it as a spring mass system. For Tracker, we tracked the center of mass as the object swung around in an oscillating shape. It can be shown using the red little dots as it started to create an ellipses type shape. And then on the right, you can see how it was plotted in the X and Y positions in accordance to time. Here we have some calculations that we were able to do using the data we got from Tracker. In the top left, we have our oscillation period using the Y values to get our variable T, which we then plugged in to find the spring stiffness, K, which is equal to 4 pi squared times mass divided by T squared. And then we used what we got for K to find the length, which equals the total length minus mg over K. Using the calculations from the previous slide, we inserted this into our GlowScript code. We were already given the mass of the system, and then we also had to adjust the time, the spring constant from our calculation, the relaxed length of the spring, which we also calculated, and we had the constant gravitational force, which is always 9.8. And then we also had to edit the lines to figure out how to change these values and compute the different types of energies, which are based off their formulas. To get kinetic energy, we had to do 1/2 times the mass times the magnitude of the ball's velocity squared. And then for gravitational potential energy, it was mass times the gravitational force times the position of the ball at Y. And then the spring potential energy is 1/2 times K stiffness S squared, and then the total energy is kinetic, gravitational potential, and spring potential energy all added together. These are very important and are needed in the end. Here our GlowScript continues, as it is important to define the initial energies and to fix the calculations for gravitational force, spring force, and net force. And to also apply the momentum principle. We also needed to update the spring and calculate the energy changes. Here is the GlowScript results. As you can see, the green line is the change in spring potential energy, the red line is the change in gravitational potential energy, the blue line is the change in kinetic energy, and the orange line is the total energy. Now, since the total energy is all the spring potential, gravitation potential, and kinetic potential energies added together, you can see that it is about 0, which it should be. It is also good to point out that the spring potential energy and the gravitational potential energy are opposites. about. As we continue looking at the results, you can see that the red is the actual, while the blue is the computational data. And the main reasons for differences is the blue had no drag, and there was also a human error in picking the center of mass for the actual. So while normal systems would slow down and get slower, the computational just kept it at a constant rate. For our model system, it did satisfy the energy principle, which is the change in total system of the energy must be equal to all the energy transfers with the surroundings. Since the spring doesn't transfer any energy, there's no work done / energy transfer, so the total is equal to 0, which, as you can remember before, that orange line was about at 0. And then also you can note the differences in the X and Y oscillation periods, where X is about 1.61 seconds while the Y is 1.51 seconds. And it is important to note that this is simply an average calculation done over 3 oscillation periods. And this is because the motion is wider than it is short. And that concludes my presentation.